Hello again, College Algebra students. This is going to be Chapter 1, Section 2, and we're going to be looking at applications and modeling with linear equations. So we're going to be using the linear equations that we learned about in the last section, and then we're applying them in word problems. I know many of you don't like the idea of word problems, but we must look and see how they are applied in the world, so you can better understand why we have them. In this section, we'll be looking at solving applied problems, so like I said, word problems. And then the types of applied problems that we'll be looking at are some geometry, motion problems, and some mixture problems. There's 4 examples I have for you. Let's get started. Hello again, College Algebra students. In this section, we'll be looking at Chapter 1, Section 2. These will be applications and modeling problems with linear equations. We'll be applying the types of linear equations that we had solved in the previous chapter in different ways. So the different ways we'll be looking at them are through geometry problems, motion problems, mixture problems. And whenever I say application problems, this means we're looking at word problems. So I'm going to try to make this as painless as possible and easy as possible for you. So just bear with me. In this solving applied problems, these are the steps that we are normally going to take. And these same steps are written in your book if you want to read it. Okay, step 1, we're going to read the problem carefully. And throughout the whole problem, we may need to reread it over and over several times to arrive at the solution to the problem. And then step 2, we assign variables to what we are solving for. Step 3, we write an equation using the variables that we just obtained from the second step. Step 4, we solve the equation. And step 5, state the answer to the problem. And in this step, we ask ourselves, does this answer seem reasonable? And that is all part of step 6 in checking our answer. So let's get started with this first example. This is a geometry application. Let's read it. The length of the rectangle is 2 inches more than the width. If the length and the width are each increased by 3, the perimeter of the new rectangle will be 4 inches less than 8 times the width of the original rectangle. Find the dimensions of the original rectangle. Right off, I know I need variables for my original width and original length, and we're also going to be dealing with a new width and a new length for our new perimeter that we're going to be using. So let's just put these all down. It says at the top here, the length of a rectangle is 2 inches more than the width. This is referring to our original length and width. I'm going to denote this by WO. And nothing changes about the width, as you can see. The length, though, is 2 inches more than the width. So let's just call WO X. And then our original length, we're going to say it's equal to X, because it's our width, plus 2. And then this next portion, it says that the length and the width are each increased by 3 inches. Let's just deal with that for now. We're going to increase our original width and original length by 3. So we're going to get our W, sorry, I'm going to call it WN for new. Our WN is going to be x plus 3, because it's been increased by 3. And we're going to do the same thing to our length. So our new length is going to be x plus 2 plus 3. So x plus 5. Okay, now that we have our new width and new length to go along with our perimeter of our new rectangle. So it says perimeter of our new rectangle will be 4 inches less than 8 times the width of the original rectangle. So what I'm going to do here is use our perimeter formula. Our perimeter is equal to 2 times the length plus 2 times the width. And we have information about our new perimeter, but no information about our original perimeter. So what we have to do is plug in our new width and our new length into this formula. And what we're going to end up with is, I'm going to call it our new perimeter. So what goes in for our LN, oh, I stated that twice, I'm sorry. Our LN and our WN are the x plus 3 and our x plus 5. So we're going to want to figure out what is x. Okay, so going from there, our new perimeter is equal to our 2 times the new length plus 2 times the new width. And we know our new length is x plus 5, and the width is x plus 3. Now let's just distribute and combine terms. I'm going to skip a step and just say RPN, new perimeter, is equal to 4x plus 16. Now, on the previous page, it said that our the perimeter of the new rectangle will be 4 inches less than 8 times the width of the original rectangle. So, our new perimeter, which is this right here, 4x plus 16, is equal to 8 times the original rectangle. So our original rectangle was just length x, so 8 times x, and then it's 4 inches less, so say minus 4. And there we have our equation finally. And this is the equation that we're going to be using and solving for x. And then we're going to figure out what our dimensions are of this original rectangle. Let's solve. So subtracting 4x and adding 4 to both sides, here's what we end up with. And so our x is equal to 5. Now if you remember from a previous page, our original width was just simply x. So x is equal to 5, so our original width is 5, and it's measured in inches. And our original length of this rectangle was x plus 2, So x plus 2, 5 plus 2, that gives us 7 inches. So there we have it. Our original dimensions of our rectangle. We just found them. Alright, the next type of problem that we're going to be looking at are motion problems. And here's some hints about motion problems. I'm just going to read it off to you. It says, in a motion problem, the components distance, rate, and time are denoted by the letters D, R, and T, respectively. The rate is also called speed or velocity. So in your problems, in your word problems, you may read speed or velocity. Just know that is your rate, okay? That's what you're going to be putting in for R. So here rate is understood to be a constant. In other classes such as physics, or maybe you studied in your physical science class, there's other forces in nature that can act on the velocity. And here we're just understanding that rate is a constant rate and nothing is changing it. So know this formula right here. D equals RT. Distance is equal to rate times time. And here's some other related forms. R is equal to D over T, and T is equal to D over R. Okay? Here's our example about motion problems. So let's read. Carissa drove to her grandmother's house. She averaged 40 miles per hour driving there. She was able to average 48 miles per hour returning, and her drive time was 1 hour less. What is the distance between Carissa's house and her grandmother's house? How I'm going to show you how to do this is I'm going to make a table of values here that we know. But first, our distance is what we are trying to find here. The distance going to her grandmother's house and coming back to her grandmother's house are the same. So I'm going to say let our distance here between the two houses be equal to x. And here is our table I'm going to create. We're going to have our rate in one column, our time, and our distance. And I'm going to split it up. One is going to grandmother's house, one is leaving or returning home. Like I said, it's the same distance there and back, so x. And that's what we're trying to find. Our rate going is up here, 40 miles an hour. And our rate returning, right up here, 48 miles an hour. And using the different forms of the distance formula, distance equals rate times time, we can figure out what t is here. T is equal to d over r. So t in this place, we're going to say it is equal to, let's see, our distance is x over our rate, which is 40. Same thing for the returning spot here. Distance x and rate 48. Okay, so I like using a table. It makes things a little bit more clear on what you're trying to figure out. And let's go back to the problem. It says, what is the distance between Carissa's house and her grandmother's house? Well, this isn't going to get us much of anywhere. But this column right here, what we're going to do with it is set up an equation using this column right here. It says she was able to average, up right here, she was able to average 40 miles per hour returning, and her driving time was 1 hour less. So how we're going to set this equation up is just like this. Our time going there is 1 hour less, and that is equal to our time returning. Okay, so here we have our equation. Now we just need to solve for x. What I'm going to do in this case is, like we did in the previous section, multiply by the least common denominator to get rid of all of our fractions. And to simplify things, what our least common denominator, what I'm going to say it is 40 times 48. Okay? And so multiply both sides by the 40 times 48. And then distribute it. When we distribute that, what we end up with is, well, the factors of 40 actually end up canceling out here in this case. So we end up with 48x minus, now we need to distribute the 40 times 48 to that negative 1, which is going to give us 1,920. Alright, and now, again, on the right side of the equation, the 48's end up canceling, so we end up with 40x on this side. Now no fractions to deal with, and we simply solve for x. Now I'm going to subtract the 48x from both sides to get negative 8x. Now divide both sides by that negative 8, and we get x is equal to 240. So if x is our distance, then our distance from Carissa's home to her grandmother's home is going to be this amount right here. It's going to be measured in miles. So our distance is equal to 240 miles. That is our answer. Alright, deals with mixture problem. It's a mixture problem. And here's a hint about mixture problems. It says, in a mixture problem involving solutions, the rate or the percent of concentration is multiplied by the quantity to get the amount of pure substance present. Okay, so you'll see in the next example that I have for you that we're going to be dealing with mixing solutions together. And they each have a concentration. Okay, and then this hint right here. The concentration of the final mixture must be between the concentrations of the two solutions making up the mixture. So say I have a 5% solution and I'm mixing it with a 15% solution. Well, it's not going to be any greater than 15, and it's not going to be any less than 15 whenever I mix those two solutions together. It's going to be between those two solutions, somewhere between 5 and 15. Okay, So that's just the hint there is what that is saying. Let's look at this. Alright, so we're asked to find, it says how many gallons of a 25% antifreeze solution should be added to 5 gallons of 10% solution to obtain 15% solution. Okay, so what I'm going to do here again is set up a table of values. Okay, I'm going to label these table of values for you. What I'm going to say here is let the, need my writing tool, let X in this case be equal to the amount of our 25% solution. Okay, because we are wondering how many gallons of this 25% solution of antifreeze should we add to the 5 gallon of 10% solution. So this is our X, this is where we're going to use our X amount. Now, let's make a table to make things come together a little easier. In my table, I'm going to have strength. It's the strength of our solution, so 25, 10, and 15%. And then how many gallons of each strength we have of each solution. So gallons. And then last is going to be gallons of pure solution. And like that hint said, it's going to be our strength times the amount of gallons of that solution that we have. So we'll get to that in just a second. Gallons of pure antifreeze. Okay, those are the 3 things that we need to figure out here. And our strengths, like I said, it's 25%, 10%, and 5%. And then we already said let X be the amount of 25% solution, so the amount means gallons of solutions. That's going to be our X. We already know that we have 5 gallons of 10% solution, so let's write that down. And then we're mixing these 2 solutions together to get our, meant to write 15%, to get our 15% solution. So what we're going to do here is add these 2 gallon solutions together. So say X plus 5. That's our mixture, adding these 2 solutions. Alright, now for this last column here, gallons of pure antifreeze, what we're going to do is multiply together our rows here that we have. So multiply across to get the amount of gallons of pure antifreeze. So 25% times X, change the percents to decimal, so we get 0.25X. And then here, 10%, so 0.10 or 0.1 times 5. It's going to give us 0.5. And then again, 15% times x plus 5. We'll distribute this later on whenever we write our equation. I'm just going to write it out. 0.15, that's 15%, times our x plus 5. Alright, so to write our equation, what we're going to do is use this last column here. This last column of information to come up with our equation. And how we're going to do that is, well, we're mixing two solutions together to obtain the other solution. So we're adding two solutions together to obtain the other. We're going to add these two rows together, and it should equal our last one. And that is our equation. Okay? So I'm going to go on to this next slide and we'll write out our equation. This is our equation right here. The first row, last column, plus the second. Oh, I already multiplied those together. Let me erase that. Those two solutions added together is equal to our total solution. So this here. Alright, now we have an equation to solve. Let's solve this. First, do our distributing. And we get this here. Let's see, 0.15 times 5, 0.75. Now, combine like terms, or sorry, not combine like terms, add and subtract things from both sides of the equation. And what we're going to end up with after we do that is 0.1x is equal to 0.25. And when we divide both sides by the 0.1, this is what we're going to get. X is equal to 2.5. Now, x, if you remember, is the gallons of 25% solution that should be added to our other solution. And so this is what we needed to find. So what x represents is we should add 2.5 gallons of the 25% solution to obtain the 15% solution that we are wanting. So there we go. There is our answer. Alright, I think I have one more example. Yes, and it's another mixture problem, but not like the previous one. This deals with investment and mixing two investments together. And here's a hint for this. It says, in mixed investment problems, multiply each principal by the interest rate and the time in years to find the amount of interest earned. So the formula that we're going to be using here in this problem is our simple interest formula, the I equals PRT. And we'll apply that in this next example. So this example here says last year Owen earned a total of $784 in interest from two investments. He invested a total of $28,000, part at 2.4% and the rest at 3.1%. How much did he invest at each rate? So we're trying to figure out how much he put in to invest at 2.4 and how much he invested at 3.1. You may think we may not have enough information, but we really do. Like I said, we're going to be dealing with the formula I equals PRT. Okay, so let's make a table of values like we did in the last one. We need to know our principal, and we need to know the rate, and we need to know time, and of course our investment amount. Okay, so for this first one, I'm going to say that P, our original amount, well, the part amount that is going to be invested at 2.4%. Let's go ahead and put our rates down. 2.4%, change it to decimal form, is here. And then our other one, 3.1% here. The principal amount that's going to be invested at the 2.4%, let's just call it X, because we don't know how much is being invested at that certain percent. But we do know the total amount that's being invested. It's $28,000. So let's say that our principal amount for this 3.1% is going to be our original amount that our total amount that we're investing minus the investment amount at the 2.4%. If this doesn't make sense to you, let me know in person and we'll go over some more. And then it says in the problem that it says last year. So this whole time that has been passed, that has passed, is just a single year. So that's what goes in time, is 1 year. And for I, what we're going to be doing here is, like our previous mixture problem, is multiplying all of these things that we have in our columns straight across, and because of this formula right here. So let's look at that. I is equal to PRT, so multiply X times 0.024 times 1, and we get, oh, not that, let's erase it. .024 times X. And then the next one we get, when we multiply straight across all the columns together, you get 0.031 times our 28,000 minus X. Now the problem did mention one more thing. It says that the total interest earned is this $784. So we do know that this total interest is going to equal the $784 when we add them together. So what we're going to do is add these two rows together, and it should equal our 784, and that is going to be our equation that we use. So let's move on. So here is our equation. We're adding together this investment amount plus the next one. And that is equal to our 784. Now solve for X. First distribute, as always, when there's parentheses. And we end up with this amount here. And I'm going to skip a step and I'm going to combine like terms. So we get 868 minus this amount here. And that's equal to our right side of our equation. Now, subtract the 868 from both sides. Gonna get negative 84. And then divide both sides by the negative 0.007. And we have our value for x is 12,000. Okay, so the amount that was invested at the 2.4%, that was equal to our x. That's our principal amount. So here's one of our solutions. So what we're going to say, I'm going to write it out in sentence form here. Sorry about the bell again. Owen invested $12,000 at our 2.4%, and then to come up with the other amount he invested at the 3.1%, we just need to subtract the 28,000 and then 12,000. So we get 16,000. And that is at the 3.1%. And there we have it. There's our solutions. I think that is the end. Yep, that's example 4. So until next time, bye.